Hey everyone, it's Dr. C. Happy Friday. Um, just to let you know, we have a little bit more to do in the kinetics chapter. We are almost done, which is good. So we've covered thermo. Is a reaction going to happen? Now we've talked about rate of reaction, what impacts rate, how does concentration change over time, that kind of thing. And then we're going to go into, over the next month or so, we're going to focus more on equilibrium. We kind of lie to you for most reactions and say reactions go to completion. Well, in reality, some reactions do, but in reality, many reactions reach a state of equilibrium where we have both a forward reaction and a reverse reaction. And so we'll get into that probably on Tuesday. But let's get close to wrapping up the kinetics chapter. And this is where we left off. We left off with the integrated rate law. All right, and again, this is a modified form, if you want to think of it as the rate of the rate law, which is concentration and rate. This is really, concentration and time. How does concentration change over time? And we can come up with these equations for a zero, first, and second order. Now, for this course, we're focusing on the simplest reaction. All of these equations that we've come up with here for zero, first, and second order are all for one reactant going to product. Okay? If you go on in chemistry, particularly if you take analytical chemistry, you will look more deeply into kinetics and you will look at more complex reactions. Not terribly more complex, but say two reactants, A plus B going to products. And the rate laws would look different. Okay, just to let you know. So make sure you know, I will always give you these integrated rate laws on an equation sheet for an exam, but you need to know which one is the zero order, which is the first order, which is the second order. And they're pretty easy to pick out. The first order one has natural log in it. The second order one is 1 over concentration. And the zero order is just concentration. All right. And the nice thing about all of these is that these are written in their linear form, y equals mx plus b. So we can always prove a reaction order by making a plot. All right, and the one that you're most familiar with that you needed to know for this exam that we just finished is the first order plot, where our y value is natural log of the concentration, our x value is time. If the reaction is first order, we should get a straight line with a negative slope. Okay, so that slope will equal the negative of the rate constant. So we'd have to take that slope and change the sign to determine our rate constant. Okay, so you should know that one. And here's just a different form of that same equation. All right, we did talk a little bit about the second order one already. This one, to prove second order, 1 over concentration versus time. You also saw that in ALEKS as well. This one has a positive slope, and so in this case our slope directly equals our rate constant. Now we really haven't talked much about the zero order one yet, and we're going to focus mostly on first and second because those are the most common, but the zero order one you should recognize. This one just has concentration and time. Okay, and if it's zero order, so if zero order, you should get a straight line. This one also has a negative slope, so you're going to have to change the sign of the slope to get the rate constant. Now, you might be looking at this plot and say, wait a minute, I thought concentration versus time was a curve. Okay? And that's generally what we see, a curve. So make sure you know that. Generally, for first or second order, as we have higher concentration of reactant, the reaction is faster rate. Okay? More molecular collisions, faster rate of reaction. As the concentration of reactant drops off, less collisions, slower rate. And that's why we generally see a curve. Now remember, zero order is kind of a special case where the rate is constant. Okay, the rate is constant. So for zero order, now I'm writing maybe too much on the screen and it's all over the place. I apologize. Zero order for one reactant going to product. Zero order, we just end up with that goes away. That's just one. Rate is constant. And that's why for zero order, if we do concentration versus time, it's not a curve, it is linear. All right, because the rate stays the same even as reactant concentration decreases. Okay? All right, so make sure you know those. All right, and then the last thing for this chapter that we have started, and see if I can actually get to that, is half-life. Okay, and half-life is a pretty simple concept. The time required, oh, that's my neighbor's dog barking outside. I don't know if you can hear that. The time required for the concentration to be cut in half, essentially. All right. Now, we did go through in class, I think, maybe at least in one section, how to derive this. I think I ran out of time in the other. This is one form of the first order integrated rate law. We can write it even a different way. If I flip my A naught and AT, okay, so in the equation there, AT is in the numerator. If we flip those, that will change the sign of the other side of the equation. It's a little easier to then say, well, let's plug in the concentration at that later time, which in this case is T1 half, is going to be the initial divided by 2. So if I do that and I plug into this equation, I'm going to have the natural log of the initial divided by the concentration at T1 half, which is the initial divided by 2, and that will equal to KT1 half, because the time is the half-life, okay, where that concentration is half. And our initials will cancel, and we're going to end up with 1 divided by 1 half, which is natural log of 2. So 1 divided by 1 half is 2, is KT1 half. Let me scroll down just a little bit here. And we end up with the first order half-life equation. Natural log of 2 is 0.693 divided by the rate constant. So this is first order half-life. All right. And as you saw in ALEKS this week, you can rearrange this. Quite often, we'll use the half-life to solve for the rate constant. Okay, so knowing the half-life of the reaction, we can solve for K. So you would just need to rearrange this equation. 0.693 divided by the half-life will give you that rate constant. All right, so the first order half-life is actually kind of cool. You might not think so, but it's kind of cool because there is no concentration in that equation. Okay, now that may or may not surprise you, but the concentration cancels out. All right, so what that means is our half-life is independent of concentration at any point in that reaction. And this only applies to first order, so make sure you know that. Concentration does not affect the half-life for a first order reaction. And what we mean by that, the half-life is constant and independent of concentration, as you see here. So here's our starting concentration, 1 molar. The first half-life is the time it will take for the concentration to be cut in half to 0.5 molar. For this reaction, this is first order, it's going to take 100 seconds. Once we know that, we know for first order that every subsequent half-life will be 100 more seconds. Okay, so to go from 0.5 to half of that, 0.25, is another 100 seconds, 100 to 200. To go from 0.25 to 0.125, so cutting that concentration in half again, guess what? It's another 100 seconds. That's unique to first order. And that's really cool. Once we know the half-life, every half-life is the same amount of time. Okay? Now realize every time we're cutting the concentration in half as we go. All right, so we've already just talked about this. Same amount of time to go, say, from 2 molar to 1 molar as from 1 molar to 0.5 molar. That's unique for first order. Make sure you know that. All right, so we'll talk about some applications in class on Tuesday, so let's save that. So let's do one more thing for this pre-lecture. Okay. And actually, if I have time, I'm going to get to a problem. I've gone for about 9 minutes. Let's look at the second order integrated rate law, which is 1 over the 1 over the concentration at some time, positive slope KT plus 1 over the initial. Okay, again, make sure you can recognize that equation. Don't have to memorize it, but if it's on an equation sheet, you need to know, boom, second order. All right, now, again, at the half-life, the concentration at T1 half, sorry, that says T1 half, I apologize, is the initial divided by 2. So we can substitute in here okay, so I'm just saying at the half-life, this should say half-life here, so at T1 half, the concentration is going to be half of the initial. So now when we, in effect, if you look at the 2 down here in the denominator, we're taking 1 divided by 1/2. So this is going to give us 2 over the initial. Okay, so hopefully you're still with me there. So now we're going to subtract minus 1 over the initial from both sides. So I'm going to subtract 1 over the initial from this side. That's going to go away. 2 over the initial minus 1 over the initial is just going to leave 1 over the initial concentration. Okay, so check that math, that you can get that, is KT1 half. All right, and if we then divide by K, we're going to isolate T1 half is 1 over K, the rate constant, also divided by the initial. All right, and what do you notice? The difference between the first order half-life and the second. Yeah, it is concentration dependent. It is concentration dependent. All right. So make sure you know that. So every half-life, so what we're going to find for, and I'm going to put these calculations, I'm going to show you, I should have opened this Word document before I started my pre-lecture. But maybe I will put these in the quiz and you can see if you can get these right. So where is that? God, I have so many documents, it's crazy. Let me see if I can find that. I apologize. All right. So let's talk about second order and let's talk about half-life. Okay? So in this one, it tells you it's second order. And I think I'll wrap up with here for the pre-lecture because I'm 12 minutes in. Second order. So that tells us second order, if we're going to talk about concentration and time, as we have concentration, we have time, we're going to need the second order integrated rate law. But this is talking about the initial concentration is this. What is a concentration at a later time? All right, so that would be the second order integrated rate law. We'll take a look at that in class. But since we stopped with half-life, one thing that I'll put on the quiz here is have you look at the half-life for a second order reaction, which we just saw. T1 half is 1 over the rate constant and also divided by the initial. All right, so look back up here. To get the half-life, you just need the rate constant right there, 0.54. Substitute that in. Substitute in your concentration and solve for time. Okay, that'll be a question on the pre-lecture quiz. Now we're going to plug in for the next half-life. So, this would be one half-life to go from 6 times 10 to the negative third to 3 times 10 to the negative third. Now it's asking, what is the half-life? This would be, if we start at 3, what would be the time for it to be cut in half, which would be to 1.5 times 10 to the negative third molar. All right. See what you get here, but these half-lives will not be the same like a first order one is. All right, because our concentration is now smaller. See what that does to your half-life. Okay? All right, I think I will leave it off there. So this pre-lecture might have questions about what kind of plots you would do for 0, first, and second order. It might have some information about half-life for first order versus half-life of second order. I'm definitely going to put these 2 calculations on there. Try to make it easy enough for you. But make sure you get prepared for class. We have a little bit more to do with integrated rate laws. We're going to talk a little bit about doing radiocarbon dating here with this problem, which is pretty cool, but let's save that for class. All right, I will see you on Tuesday. Take care.